try to keep you awake after lunch, so I'll try to keep this as interesting as possible. So I gave yesterday a talk a little bit about the ARENA project, which centers around RENA, and Paul also asked me to give a presentation which is built upon our proposal, which sketched a little bit what went wrong in the history of what we currently have in the architecture, and how we came to this, well, not me, but John Day, how we came to this RENA architecture. So I'm going to guide you a little bit through the history of the internet and where things went wrong, and why we think you need a new architecture, at least if you want to have a scalable solution. So this is a quote from, paraphrased from Dimitri. If you haven't seen it, you won't get it. I apologize. But I hope at the end of my talk, this will make sense to you. So let's start. So first I'm going to diverge a little bit about the nature of layers. So where do network layers originally come from? So actually in the very early days when so this is Leonard Kleinrock with the very first internet messaging processor or something, the IMP. So in the early days, packet switching required. Sorry? Yeah, I'll come to that. So you can answer the question when I'll answer. So the very early days, packet switching required quite complex software for that time. And when they tried to implement that, they looked at the next most difficult pieces of software that they had, which were operating systems. And operating systems in there had layers of programming, but there's one difference. In operating systems, layers are really a convenience. It's just for managing the complexity of the software. And as we'll see later, in networks, they really are a necessity. You cannot have networking without layers. So very basic question, what is a network layer? Anybody who has a good answer to what a network layer actually is? Don't be ashamed, nobody knows. So you have the OSI model, which has a physical layer. The functionality is just to provide a medium for transmission. Then you have the data link layer, and its functionality is just to provide transmission between the endpoints, so to manage transmission between endpoints of that physical medium. Above you have a network layer. At that point, you really have networking. You have multiple hops that you can traverse with your system, with your signal. Above that layer, the OSI says you have a transport layer. The function is really to do end-to-end transport management. Then we have something called a session layer, a presentation layer. And I all see you thinking, what's their function? Nobody knows, nobody cares. And on top, we have an application layer. This is one way of looking at layering. We are in transport networks. You also have seen layers like this. You have an optical layer. On top, you have an IP MPLS layer. There's also talk about a control plane, a data plane, and a management plane. So actually, the definition from OSI for a layer is that it is a collection of subsystems of the same rank. And it says subsystems are the intersection of a system and a layer. That's quite a circular definition if you ask me. So even the OSI guys don't know what a layer is. So actually, these are not the layers you are looking for. If you want to have a scalable network, this is not the way how you would organize the layers in your network. So the important thing about layers is that networks, they have a number of they have systems which need to distribute shared state with different scopes. So at least you will have a different scope means a different layer. And if there are multiple layers of the same scope, their functionality must be independent, because else you would have two layers trying to share state between the same endpoints, which doesn't really make sense. You want to centralize all those functions, or at least keep the functions in the same layer. So for instance, if you look at what is currently our architecture, is you have roughly this architecture, but the data link and the network layer right now have mostly the same scope. So there are some issues with the current architecture. So what's wrong with it? Well, you all know we are all researchers in networking, which means there must be some issues with it, or else we would be out of a job. So there's weak security, can't argue with me on that one. There's explosion in the complexity of the overall system, and scalability with, so there are scalability issues with the routing system. So this is a very famous picture of the number of BGP entries, which isn't scaling linearly but exponentially. So the system is really too complex for what it should be doing. If you have a linear number of addresses, you should have a linear progression in the complexity of the system. There's no QoS. A lot of things wrong. So what are the causes of these problems? A lot of papers, research papers, they go, yeah, the requirements have changed and the internet is no longer capable of coping with them. Sounds reasonable, but we don't really think that's it. So they are not the main reason behind internet problems related to multi-homing, mobility, security, and QoS. The real problem is that it was just a first demo. The ARPANET, which was a very small network, it had a certain technology. The industry took over, they tried to build it bigger and bigger, and they always have been, when you run into a scalability problem, they try to patch around it, but never rethink, is this really the architecture we are looking for? So there were efforts in the 70s, like Cyclades network and the INWG, which were headed in the correct direction. They have an internet architecture which is quite different from what we have right now. So in 1969 was the start of the ARPANET. There was a message sent from UCLA to Stanford by Charlie Klein, and that message was?
About forgotten razor.
It was low.
Well, it's another first message.
It was low. Actually, he tried to type login, but when he got to the G, the system crashed.
No, I meant the message which Kleinrock sent, not this guy.
No, that was really the first message sent over, and 1 hour later they managed to log in onto the remote system.
Kleinrock message was sent from Europe to States.
Could be. So, and on December 5th, 1969, the ARPANET had 4 nodes between Utah, UCLA, Stanford, and I think Berkeley. So in 71 it expanded a little bit, and in 72 they encountered one of the first problems with their ARPANET architecture, that's multi-homing. So this is a satellite image of Tinker Air Force Base, and in 72 they wanted to connect to 2 different of these routers. These IMPs are now we call them routers for redundancy, and the designers they realized that they couldn't really support this feature. So if you want to route, they were naming these interfaces like we do now, and they couldn't support multi-homing to the nodes from their network, so they had to move around it. Because 2 interfaces of the same host had different addresses and the ARPANET had no way of knowing that they belong to the same host, it was left for future work, and as we all know, future work tends to stay future work. So the network grows, had international connections, and in 1972 they started a group which is called INWG, and it was guys from ARPANET, guys from Cyclades in France, guys from the National Physical Laboratory in the UK, and their goal was to build an international transport protocol, because there were London and in the UK there were hosts trying to join the ARPANET. So they had 2 solutions, INWG 37 and INWG 61. I don't know the details, so I'm not going to tell you. But they proposed a synthesis in 1976, which was voted for the architecture for the internet, so an interconnection of networks with ARPANET and other research networks. And it looked like this, so it had 3 layers of different scope. They had a data link layer, they had a network layer, and they had an inter-network transport layer. And each had addresses. So the internet model looked like this. So you had an internet layer which is addressing hosts and the internet gateways. You have several network layers of different scope, possibly different technology, it doesn't matter, but you had inter-domain routing at the internet layer. You had intra-domain routing at the network layer with different addresses. They were based on the IP or TCP protocol at that point, because it wasn't split, it was one protocol, TCP IP. And the intra-domain was really NCP, which was running in the ARPANET, which had 8-bit addresses. So, and the data link layer with the smallest scopes were the addresses for the devices, and the scope, so the address size went up when you went up in the layers. So that was the model. In 1978, they decided to split TCP from IP. And these initial versions, they performed error and flow control, TCP, and relaying and multiplexing in the same protocol. That was originally TCP IP. It was one layer, it weren't different layers. So they had the same scope, it's network scope between end hosts in the network, but still they decided to split it, and it would not be a problem if, at the very beginning, the two layers were independent and they didn't contain repeated functions, but they are dependent and they do contain repeated functions. So one of the problems is that you have retransmission in TCP and you have fragmentation in IPv4. They worked a little bit around it in v6, but that's why I said v4. I got the remark before. So you had fragmentation. So actually when you have a fragment which gets fragmented in a router between your endpoints, IP needs to reassemble the fragments in the next hop. So it will wait for something called the maximum packet lifetime, so it's 5 seconds. So it will sit there waiting for 5 seconds for all the fragments of that one IP datagram to receive. But TCP, which is running on top, connects times out a lot faster. It doesn't receive an ACK, which is typically on the order of the return trip or the return time between the end hosts. So it will engage a retransmit of the entire packet. The next hop, because the MTU is smaller than the original host starts, it will fragment again. So the next hop has two incomplete IP packets now, because it's constantly losing only one fragment, and TCP is acting a lot faster and trying to resend the datagram. So actually these two protocols, TCP and IP, should be aware that TCP knows, okay, IP is still in a waiting state. I should wait for sending my ACK until that IP times out, or I should tell IP to drop the entire packet. I will retransmit. But having the two like they are at that point it doesn't really make sense. So IPv6 does support fragmentation, but not in intermediate points. So you have to say it will do an MTU discovery, and you have to fragment your packet at the starting node, and then you don't run into this problem anymore. But still, the problem exists. So in the meantime, ARPANETs kept growing. That was around 77. And then in 1981, there was a fundamental paper by Richard Watson, which is called Delta T, which is a protocol, which is a reliable transmission protocol, similar functionality as TCP/IP, and it has a very unique approach. It just assumes that all connections exist at all the time, but it only keeps the state for connections which have a recent activity. And he proves that you can have distributed synchronization if you have only 3 timers which you are bounding. So the maximum packet lifetime, if you don't bound this, means when you send a packet, it's remote storage, so it doesn't need to arrive at the end host. You have a maximum number of retries that you do. So if you don't receive an ACK, so you have the waiting time before you ACK, so the maximum number of retries before you assume that the connection is dead. And then you have a maximum time before you send an ACK. If you bind these 3, then you have reliable transmission. So the only thing that you need is SYNs, FINs, and these 3 timers. There is no explicit, so you don't need SYNs and FINs, you only need the ACK and the 3 timers. So there is no explicit state synchronization. You just assume that the state that the connection is alive until all these timers time out, and then you assume it's dead. So you don't need this SYN. So all properly designed data transfer protocols should be soft state. You don't need any hard state to maintain. The only thing that you need to maintain is 3 timers. And Watson also proved it in a paper that TCP has these 3 timers, has the ACKs, but it has a lot more. So it's really a little bit redundant. You don't need the SYNs and FINs in TCP/IP. And another important paper was around 1982 from Jerry Saltzer, and we published as RFC 1498 in 93. And it's just a general paper which is discussing the nature of naming and addressing. So it has really 3 different entities which you have in your network. One is names, which are what you're trying to reach, and they should be location independent, because if they're location independent, you're blocking your mobility. So it just, if I want to reach Anna, I don't need to care where Anna is. I just know it's Anna, so the network needs to figure out where she is. So addresses say where, so the network will need to resolve the address of Anna before I can send her a message, and the routes will also be determined by the network. It's how to get there, and this needs to be route dependent, and it needs to set a number of hops between the end nodes, very similar to what is currently happening in the internet, except that there's a very small tweak that needs to be done. So 4 things need to be named: the services and users, we call them applications. It's the application process that you want to reach in the network. You need to name your hosts, you need to name your points of attachment, which are the interfaces, and you need to name the routes. You need to say, I want to go over this set of nodes. So the network view of Salter is that your application name will map to an address, so you need to resolve the address of an application. The node addresses map to point of attachment addresses. To go in the layer below, you select your interface towards the next hop, because in a network you can have multiple interfaces between the same hosts and multiple paths, and yep, that's basically it. So on 1983 there was something called Flag Day, and that's when they decided that the protocol will be TCP/IP, and they moved for the ARPANET towards TCP/IP. But this is the INWG model, and it had 3 layers. What they thought the internet should look like: you have a data link layer, you have the network layer, which is based on the NCP of ARPANET, and on top you would have an internetwork layer based on TCP. So what actually happened is the internetwork layer, TCP/IP, went into the network layer, and the internetwork layer, where's that? We don't have an internetwork layer anymore. So that's why I say there is no internet, because we don't have this additional level of addressing between networks. We have some ways of figuring patches and things like that. Oh, BGP, which is really using also the same address space as IP, but it's not an additional layer in that sense that it doesn't have addressing, it doesn't have routing. So even the simple model of 4 layers, you have physical data link network and transport. In the real world, that's not even it. You can have a very complex interworking of all different types of layers, and it's very hard to manage. So 1983, something went wrong there. So the first opportunity to fix the naming and addressing was missed when they adopted DNS. So in the 70s, they had a very limited number of applications. Actually, they had 3. They had Telnet for remote terminal. They had FTP for file transfer, and then they had something called RGE, which is remote job entry, where they could do something like we call now cloud computing. You could run a job on another machine. And there was no real need to map application names to addresses. They had something called a host file, which you still have on your Windows machine, and it just said that this application has this port number. That's how they used it. So they didn't really name their application, but of course they knew that this needed to be done, that you needed to map your applications at least to an address in the layer below to do networking. However, it was also future work, and it never happened. So DNS continued to use these well-known ports to name applications. So the port numbers are completely network-wide. Everybody knows port 80 is HTTP. Port 8080 is also HTTP. Port 23 is FTP. These are all fixed. So the number of applications you could run in the internet is actually limited by the number of ports, which is an externality that you really don't want. So the DNS entry is just, you are mapping a name, a URL, and you are mapping it to the synonym of an interface of a host. So it's not even mapping it to the hosts, it's mapping it to an interface of that host. It's the same interface as your Ethernet layer, and there's a port which is really the endpoint of your TCP connection. So there's a fundamental issue that you have a static binding between layers. The application names, what should be in the application layer, is actually bound to the network layer and indirectly to your data link layer, because it really, your network address is also a synonym for your data link address. I mean, the IP address goes to your interface, not to your host. So in 1992, they had another opportunity to fix addressing with IPv6. The Internet Advisory Board wanted to have the scaling problem of IPv4, the limited address range, and they started a group to resolve this. And they had three types of solutions. They had this classless interdomain routing, which is adopted right now. So actually you are enforcing a hierarchy onto your addressing scheme, which improves scalability. Then you had the design of a next version, which would be IPv7 based on a protocol which is called CLNP. It's a connectionless network protocol. And this was from the OSI guys, not from the IETF guys. And the other one was just to continue the research and hope something else came out of the research. But actually, this connectionless network protocol was not adopted by the IETF because it was coming from the OSI world, and they weren't very cooperative with each other. And so the Internet Advisory Board reconsidered this decision. It started the IPNG. One of their rules was that they could not change the semantics of the IP address, and so they still named the interface instead of the hosts. It is explicitly stated in the RFC of IPv6. And then there was one other, but I moved it so chronologically it comes before IPv6, but I thought let's keep the IP, the addressing challenges together. So there was in 1986 the congestion collapse. What they actually did was to use the same methodology that was in the Ethernet networks with a few modifications of doing congestion avoidance, and they put it into the TCP protocol, which is layer 4 in our current internet. So the effectiveness of a congestion control scheme is really determined by the time to notify. The faster you know there's congestion, and actually if you have explicit congestion detection, that would be very good. You would be able to do the congestion control. Actually every textbook on feedback and control loops will say that your control loop should be as close as possible to your problem. And if there's a congestion in the Géant network and I'm here in NordUnet, then I would try to resolve that congestion here, while actually Géant should try to take care of that. So the congestion detection is really implicit in TCP/IP, so it's just trying to increase the window until it finds congestion, so it's causing congestion, and then it says, okay, I will try to decrease my window. So it's actually predatory because it needs to cause the problem before it can detect it, and sometimes you can have the avoidance triggered when there's really no congestion in the network. So you just have arbitrary packet loss because of whatever, just random, some errors, which are, no system is perfect. You would try to change your congestion, which is decreasing performance when there really was no congestion in the network. So, are there solutions to all these problems? Of course there are, and we know about them for a long time. So for instance, the multi-homing problem, the solution is very simple. I mentioned it a couple of times. So it's just name your nodes, don't name your interfaces, name your nodes. Calculate routes based on those node names. You will not run into the problems that you have right now. And really selecting the interface will be a local problem. I need to find the next hop. I will use this interface because I know that is the next hop. It's really simple. Did nobody realize it before? Well, ARPANET, they knew about it in '72 when TinkerAFB wanted to join it. They knew how to solve it, but didn't do it. Cyclades network, they didn't have this problem. They named the nodes, and there were also OSI, the OSI model. They really knew the nodes. So I think the CLNP protocol, they knew it, but that text went blank, so it's white instead of bold. But IPv6 addresses in the RFC says will name the interface and not the host. It's explicitly stated there. So this application naming, can we fix this? Well, it's quite simple. In the application layer, you should name your applications, and it should be independent of the addresses it gets the address the application gets in the layer below. You should have resolution from the layer below towards the up on top, but not the other way around. So it should be dynamic, maintained, which means you have mobility. Application developers shouldn't care about node names, shouldn't care about the network address. They just want their application to talk to the application at the end host. So it seems simple, of course. Did they realize it? Of course, the guys in France from Cyclades and the OSI internetwork model. They knew this they understood this problem and they solved it from the beginning. So there was one thing in Salzer's paper where they said that you need to name, because Salzer, he came from the operating system world, and in the operating system there is usually only one path in the processor, but at least at that time there was only one path in the processor between two application processors running on the same system, so there was not a lot of multi-user environment context switching. That was all not invented yet. So at that point, multi-processing, multi-core things. So at that point, there was only one path available in the computer between those two processes, and he didn't know, he didn't have this naming of the path between your, so from one hop to the next, he thought that was trivial, but it's really not. So you also have to name your path in the network or your interfaces locally. So it's a two-step process. You just calculated the sequence of nodes to the next hop, and you select the appropriate path or the appropriate point of attachment, the exact interface. So also these properties should be applied. So your application should be location independent, your node address should be location independent, but your point of attachment must be unambiguous between adjacent nodes. So this looks like the architecture that they came up with in the 70s. Is this the definitive architecture? Well, it doesn't seem to be. There's a lot of things that are not in this four-layer architecture. What about virtual private networks, which is really another layer? Why isn't it included in the architecture? What about virtual networking, internetworks of internetwork of internetworks? So they were on the right track, but they didn't see the repeating pattern and generalize it. So there, in a network, there doesn't seem to be a fixed amount of layers or a fixed number of layers that can give you every application that you want and all the privacy that you want and all the flexibility that you want. So it all depends on the scenario and the use case, and therefore the conclusion has to be that a fundamental architecture of computer networks should be recursive. So you don't have a limitation on the number of layers that you have, and they should be able to stack indefinitely. So when we put this all together, we arrive at RINA, which is the recursive internet architecture. It was, the groundwork was laid out in this book from 2008 by John Day. And it has a structure of recursive layers, and they provide this IPC inter-process communication, so that they really give you a channel between two application processes which should be communicating. The services and the application run on top of that IPC process or that IPC layer. It's a single type of layer, so every layer in RINA is exactly the same. It has the same functionality. You just don't need to implement it, but the maximum functionality of all layers is the same. And there's a separation of mechanism from policy, which means that the number of protocols drastically reduces. For instance, now there are a whole load of protocols that just do connectivity checking. You have echoes in IP, in the USPF. You have BFD protocol, but actually basically they do the same thing. They ping the end and try to receive it back. So that's the mechanism. You have a packet which gets an ACK, that's your mechanism. The policy is how fast do I send it, how many of these packets do I send, when do I trigger alarms. Those things are separated from each other. So all layers have the same function, different scope, very important, and different range, and not all instances of layers may need the same functions. So, but no layer will need more functions than what is available in the RINA API. And so it's a distributed application, and it provides you with IPC, with inter-process communication. And that's why the terminology for that layer is a DIF, a distributed IPC facility. And yeah, this would yield a theory of networking and an architecture that scales indefinitely in theory, of course not in practice. If you do an implementation, you have resources to take into account. So the naming and the addressing is taking into account all the limitations and observations that we made before. So let's skip this. So the scope of addresses is inside the diff. You have an address range which is per layer. No other layer knows about what your address space is, what your namespace is, and how you are using it. It doesn't really matter to layers on top of or layers below. Each diff has a directory that maps destination application process to the IPC process. So you have this important mapping between your application here and here. And because it's recursive, it's exactly the same here and here, and it's exactly the same here and here. So you need a discovery mechanism for the application on top, which you can reuse current solutions to do that. I mean, a DNS system would be able to do that in a centralized way. If you take something more advanced from peer-to-peer networking, you would use a distributed hash table, for instance, to do that if you have a very large network. So only the architecture is specified. Your implementation can still do a lot of fancy things, and it leaves a lot of room for designing different layers in RENA. So yeah, that's what I'm saying. All points of attachment are relative. It's really recursive. So this is the entire architecture. So your systems have a application processes running. They subscribe to different IPC processes or layers. You have a management agent, and each layer has these functions available. So you have some very basic functions. So they are actually organized in the order of dependency on the packet contents and the speed of operation. So actually here there is in our implementation, a separation between what is run in kernel space and what is run in user space. So you definitely want all these functions SDU delimiting, so really breaking up your packets, doing the data transfer, lookups for the routing table as fast as possible. That's done in the kernel. And then transmission control, retransmission control, that you can do it with, I think for us it's also in the kernel, but the requirements are less stringent. And then managing your routing information base, your resource information base, that goes outside of the kernel. So that's really in user space. It's filling up the routing table and the routing table itself, which is running. So it's the common known the common known separation between the fast path and the slow path. So there are 3 phases of operation in RENA. So you have enrollment, which really creates and distributes the information required to create instances of communication. This is something which is a little bit overlooked in current networks. You just configure your IP address and then you are actually part of that IP layer. For instance, or you can use DHCP, but that's sort of enrollment. But in RENA, this process has been thought through. You can use authentication just to join a network layer. Then there is flow allocation, which allocates the resources and checks if your communication, if the other application you want to reach first, you are allowed to communicate with it. So I'm not allowed to communicate with the NSA database, so a diff would not allow me that communication. But for others, it is allowed, so it will do that check, and it will also check if the other end, so the other application wants to communicate with me. So not only if I'm allowed, but also if the other application is winning. And when that happens, so the synchronization is complete, you would agree on a common protocol version for the application layer, and then actually the data transfer happened. So the IPC API has 6 operations: allocating the flow, writing packets, reading packets, deallocating the flow, and registering applications from a layer above or a layer below. And an important thing is that it has QoS parameters that you can give through, and this is defined in a technology agnostic way. Not completely done, so this is research which we are still doing on how you can define all these QoS parameters, so probably it will not be a fixed list, you could add them to them. And also to aid adoption, we have something called a faux sockets API, where you just map what is currently available in Linux, which is socket programming, towards this Lina library. The data transfer, it has 2 protocols. It has DTP, which is the only doing the forwarding and the So fragmentation, reassembly, sequencing, concatenation, separation. So you could call that delimitation as well. So these functions really depend on your contents of your packets, and you need to perform them. DTCP is the retransmission flow control, so the speed of your connection, and you don't really need to know what's in the packet to do that. To send an ACK, I don't need to know the contents of the packet that is ACKed. So they are loosely coupled by a state vector, as we saw for TCP and IP. They need to be aware of each other, your retransmission and your delimiting, and it's based on this delta T protocol by Watson. So the key benefits of RINA over TCP IP is that application naming, so really having addresses in your application namespace, or names, not addresses, names. It ensures mobility, it ensures multi-homing. You have support for QoS in the architecture. Because you have routing per layer, you can really tailor your layer to the scope and have, for instance, hierarchical naming schemes and addressing schemes that really make sense. So it reduces the routing table size like CIDR did for IP, but you can really tailor it to the application. You have improved security inherent in the architecture, because if you don't know what's in the layer on top, if you don't even know what its address space is, it's very difficult for you to figure out what the contents of the packets is. So if you are sniffing or snooping in one certain layer, you don't know what the contents is of 4 layers above. And the architecture, at least in theory, scales indefinitely, and you don't need additional functions like NAT boxes or middle boxes are less needed. I'm not sure about firewalls, that one we could argue about. So the adoption strategy for RINA is that you can, no migration, just adoption. We have interfaces to, well, especially towards the lower layer, so you can stack diffs on top. This is where we are right now. So Ethernet, we have diffs on top, the application on top of the distributed IPC facility, but this is also required for adoption, that you could run TCP IP on top, Ethernet below, and from that point, you just say, okay, I want to try this RINA architecture. You just put it in the middle, and you don't interrupt your application or your physical hardware. So it really should go smoothly and quite invisibly. So in the RINA timeline, I think we have 1 minute. So this is the optimistic timeline. The RINA project, which are here, so the goal is to have NRAN lab prototypes and have the first adaptation done by the research networks, and in the end try to have this all RINA networks early adoption by 2020. So the question is, are you ready for a simpler future when you don't have all this stacking of all different technologies and unmanageable layers, but you just go to one type of layer and stack them indefinitely? So that's the end of my presentation. Thank you very much, and I hope now this makes sense. Thank you.
Thank you very much. Dimitri, any question for Dimitri? I think we got our lesson.
There's one.
Just curious about, it's a recursive approach, right?
Yes.
So the IPC or IPC,
IPC.
They're all identical, right?
They are identical in function, but not in implementation.
Yeah. Then the question is, what if you want some changes? Do you need to change, like, I have a bit of a network using this, and then suddenly I want to change, I want to add an extra function. Should I just, call out all these providers and add this function to your product, and because you have this, you're using IPC and so.
Well, if it is a standardized functionality, so you will have to standardize the functionality of some diffs. If you have a public internet diff, you will have to standardize the addresses, the allocation, like is done for the IP layer. I mean, you have a fixed address, so that there doesn't change a lot. But if you want another service, you can just subscribe your application to another type of layer. You are not bound to use that specific layer. If you're allowed to subscribe to a new type of layer, which you may have implemented yourself, or it's a different service provider, you should just be able to subscribe to it. And it should be easier to design your own routing protocol. So there is one function in there, which is called the forwarding table generator. So it just says, generate a table for forwarding packets. It doesn't say do routing, do link state routing, do vector routing. Doesn't matter how you do it. You just need that function somewhere in your diff. If you have a very small one, you don't even need that function. Just broadcast over the network. So that's left open to the implementation.
Question regarding the migration from TCP/IP architecture to RINA architecture.
Yes.
Also, is it necessary to get, because I think that you have all nodes around the world should have RINA architecture implemented in their nodes in order to get there. Also, how fast you can do it actually, the migration path. Also,
It's a very good.
the end goal is actually when you have all nodes around the world running this architecture.
So yes. So the end goal. So the difficulty for the end goal is that currently we have different data link layer. So let's talk about layer 2, layer 1. So we are building a API exposing these functionalities that are available in the lower layers. We call this a shim-diff, and it's part of the migration. So that's what we have. We can stack one RINA layer on top of Ethernet. We can do it on top of TCP/IP, and we're going to look into it on doing it on top of LLC, which is also a form of Ethernet, which has an Ether type below 400. It's called LLC, which has a little bit more functionality that we need. So in terms of the adoption, we can do it above layer 2 easily, because it means modifying a protocol stack. Well, easily. We are implementing it in the kernel. It's a lot of work, but once it's in the Linux kernel, the migration could go a lot faster. But the difficulty will be on this side when you really have to rewrite device drivers. So you could expose the API directly on top of the device driver, which means you have a layer 1 RINA, and that will require adoption by the system vendors. So that would be.
It is two different ways. It is showing two different
Well,
evaluation paths, or you can both at the same time.
No, they are. You can do both at the same time actually. So this is just showing we have FP7 Irati. There we don't have applications on top of TCP/IP and implement. So we implement one direction in Irati. So we are building the migration path from the bottom up. The top down you would need to give an interface between sockets, and for instance between sockets and RINA from the top level towards the diff. So we aren't doing that now, but we should do it as well, because then you can really stack the layers into the current architecture, and in the end they should just magically disappear when people just get tired of TCP/IP.
Okay. Last question.
Yeah.
Come on,
About
Mian.
performance, maybe I'm wrong, but it looks like performance of this could be a problem, because you said it's about discovery between layers. So to me it resembles something like microkernel problem. The architecture, microkernel architecture for operating system is quite clean and simple, but the performance is a problem.
But the performance is only at the point where you need to detect the application. If the application isn't moving very fast, it's not a problem anymore, because you are routing. So you determine the address once.
It's a problem between each pair of layers. Yeah?
Ah, that you have another layer of encapsulation.
Yeah. My question is just, anybody tried to estimate the performance of this?
We are implementing it right now, and then we are going to run trials and really have applications on top of TCP/IP, on top of Ethernet, and similar application on top of the diff, on top of Ethernet, and see how the implementation works. But it's still a tricky one, because TCP/IP has been optimized for the past 30 years, and our is just a very basic lab implementation. But in general, the performance should be at least similar. So it just during the adoption, you are increasing your layers, and then you would see some degradation in performance compared to the normal network. So okay.
Thank you very much.
You'll have to use this as well.
Dimitri, thank you very much.
Welcome.
Nice presentation. So the next speaker is Mian Usman from Dante. You are part of the what's called the CTO group.
Yep.
Yep. And so Mian knows everything about the Shang network and how it has been constructed and built and how the future would look like and all the nice new stuff that will come around that we don't know anything about. So the floor is
That's
yours.
but this is not working. I can just press space, it's fine.
Sometimes it's
It's okay, I'll just press the space.
is it switched on?
I think it is, yeah.
It's power. Okay.
It's okay, yeah, I'll just use it as a laser pointer. Hi all, so as Tony said, my name is Mian Usman. I'm from Dante. We manage the Giant network, and I'm just going to give you a bit of an overview what we have done in past 2 years, the new architect, the new equipment, the migration and the convergence. So network procurement, we procured the new transmission and switching equipment, and well, it started 2011, and then we announced the vendors we are going to select in early 2012. So Infinera is now our transmission provider, and Juniper is now our switching and routing provider. So Juniper MX series equipment was selected for the switching platform. It replaced the existing Alcatel SDH for Ethernet layer or switching layer. We had Alcatel MCCs which were providing point-to-point circuits which were based on the SDH, and now we have Juniper MXs which are on Ethernet over MPLS, so we provide point-to-point services on that. One of the benefit for going to Juniper MX that we see is we can now support more services than we were able to support on the MCCs. On the MCCs we were just able to support point-to-point SDH and point-to-point circuits. Now we can support multi-point services, VPLS, layer 3 VPNs and other new services that run on over MPLS. Giant, as on the second bullet point says, Giant Plus service, which is our point-to-point circuit based service, has now been moved to MX. It is now running Ethernet over MPLS. This gives us better trunk utilization. So previously we had SDH based network. A lot of VC4s were reserved, but there was some of the circuits were not used. So we had some of the spans, we had 30 gig, 3 by 10 gigs on the route, and almost over 20 gig were reserved in VC4s, but traffic was less than maybe 2 gig even. So this gives us a bit more to play with. So we don't have to reserve the VC4s, we have IP trunks, we make better use of them. And then when we had the Juniper MXs, we deployed those, and then we've also done the convergence of the IP service with the GN Plus, because the switching layer was using Juniper MX, which could also support the IP, and IP layer was running on T series. So we've done the convergence of the two layers, and I'll go over that in a few slides. Giant Plus and Giant IP services are delivered using the new Juniper platform now. So in some of the POPs I'll show, we didn't have the T series or the IP equipment. We deployed the MXs so we can provide IP services locally as well. So convergence and this new platform deployment has enabled us to provide NREN with a single interface which they can use for multiple services, for IP, for point-to-point, for multi-point, for layer 3 VPNs as a VLAN. So why Juniper MX? As I said, the previous architect was based on the SDH, and this just gave us point-to-point services. This gives us even more multi-point service, VPLS, most importantly support of 100 gig. Obviously there were other commercial benefits as well, but these were the technical benefits that we saw and went with. It also supports routing, virtual routing. You can create virtual routers, logical systems, and of course SDN, OpenFlow. The new Junos version supports OpenFlow. The new bandwidth on demand Autobahn is running on this platform, so you can go into this nice web page, select the interfaces you want to select on the POPs and create layer 2 circuits. they run on the Juniper MX as well. Transmission equipment procurement. So we used to have Alcatel DWDM equipment that was no longer meeting our requirements, mainly the 100 gig. We needed 100 gig and it wasn't able to support it. So procurement process for that completed last year, and Infinera, as I said before, is now our transmission provider. We've completed the rollout, and Alcatel DWDM equipment is out and Infinera is in. That was completed May this year, and it allowed us to support 100 gig. So just a bit of a background where we were in 2010 and number of wavelengths that were used and why we think we needed 100 gig in future. So you can see here, this was this is what we call Western Ring. So these are the number of wavelengths, 10 gig wavelengths that we were running on the Alcatel equipment, and there were quite a lot on the Western Ring, and a lot more requirements for IP, for point-to-point circuits, and for wavelengths. So we then decided we need to move to a platform which can support 100 gig and more than that, rather than just multiple 10 gigs. Obviously elephant flows and all that comes into play on the IP layer, so it's better to have 100 gig than multiple 10 gigs. So this was the giant fiber footprint, kind of a details we had. So this is what we had to migrate. There were 5 different fiber providers: level 3, Colt, Interroute, Telia, Sonora, and Pantel. This is the distance between the huts. There were, I think, about 126 huts in total where Infinera had to go and replace Alcatel amplifier and put their own. So POP distance, there were some long route. There's one 2,000 kilometer. This one there, the only one. I think it was Copenhagen to Madrid to Geneva, or Copenhagen to Frankfurt. One of those. Most of them were between 700 to 800. So we thought when we were doing the procurement, we thought replacing switching and transmission equipment is not just enough. We need more work. So we added more work. We procured some dark fiber as well during that time. So we went with dark fiber procurement early, around May 2012. The main reason was that our lease on the dark fiber was expiring in 2015. So we're buying this new Infinera equipment which is going to run like this fiber we have, but then the lease is expiring in 2015. So we wanted to make sure that we secure a longer leases on the fibers as well before we deploy the new equipment. Plus we thought it will also help if we are able to get new dark fiber routes that we can run the parallel fibers, replace install the Infinera kit, run the new fiber on them, and then get rid of the old equipment. This way we can keep the services running on the old kit until the new kit comes in. So this really helped a lot. Obviously we weren't able to get new fibers on all the routes, so some routes were hot swap, but they went fine as well, so that was good. And now the new fiber leases, they run up to 2020, so we've got a bit of a time to go before they expire. So this is a new dark fiber footprint. This is up to 2020. So there were quite a lot of routes, new routes added. So this was one of the new route that was added: Geneva, Marseille, Milan, and these were all the existing ones. We got a parallel fiber here, and this is the one Coffee project is going to be using. They presented yesterday. We have a spare fiber here which they'll use for their experimentations, and we've got Infinera kit running on the new lease of the fiber. So while reprocuring, we also reduced some shared risk on the dark fibers that we had. So the previous dark fiber we had, there was a shared risk from Geneva. So there were 2 routes, one from Geneva to Frankfurt and one Geneva to Milan, and part of those were shared. So we took the opportunity when we were renewing the leases to see carefully and made sure that we don't take the routes or the path which are shared. So there have been one incident in the past where both Geneva Frankfurt and Geneva Milan went down at the same time. So this results in Geneva to Milan traffic going the longer way, which is Geneva, Paris, London, Brussels, Amsterdam, Frankfurt, then Prague, Bratislava, Vienna, Finkenstein, and then Milan. So this was then fixed during this dark fiber procurement. We also eliminated few other shared risks, Amsterdam, Frankfurt, Amsterdam, Copenhagen, and within Frankfurt metro area we had some shared fiber, so that was eliminated during this. So this is the example of the Geneva, Frankfurt and Geneva, Milan route. So you can see Geneva pops here, and the fiber is shared till here, and then it goes to Frankfurt and to Milan. So any fiber cut here will just take down both the dark fiber. Would have taken down. Now we've replaced it. So I'll show in the next slide. So now it's fixed. So the red one goes to Frankfurt and the green one goes to Milan. So it's eliminated majority of the risk, and it's no longer a very major issue for us. So this was the timeline. So May 2012 we placed Juniper MX order for the MCC's replacement. Almost end of July, end of June, early July, we kind of raised Infinera order, and then fiber contracts were awarded in July. First production MX, so we decided to replace the switching equipment first, and then we replaced the DWDM equipment. The main reason we did that was, once we replace the switching equipment, it is based on the Ethernet over MPLS. It can dynamically reroute the circuits. So if we are working on one span, it will find a way to reroute the circuits that are running, the point-to-point circuits. But if we were to remain on the MCCs, then it's SDH based. We'll have to enable protection, reserve VC4s, and we didn't have enough capacity to reserve VC4s for protection as well. So we first deployed the MXs. So between June and October, we deployed the MXs in about 30 POPs. So that was all the MCCs were removed. Then straight after that, we started the Infinera kit deployment. So the first XTC became in production mid of October, and end of migration was in May for Infinera. So now, while we were doing all this, we also started the network convergence around this time. The network convergence, I'll talk about a bit more here, is switching an IP layer convergence and convergence into one layer. So this work was started here and ended last month. I'll just give you a bit of overview of that in a few minutes. The first 100 gig was delivered from Geneva to Budapest for CERN 100 gig. Most of our planning for the Infinera kit from the first stage was so we can deliver this service. The first service was delivered 21st of December 2012, that was last year. So this was the very first 100 gig service that we delivered, and all our efforts were to make sure that we can deliver this on time, and that's why migration stages changed a lot to make sure the service is delivered. So network convergence, I'll just give you a bit more information about network convergence. I've spoken about that a bit in this, so I'll just go over the pre-procurement architecture, the post-procurement and deployment architecture, and how it changed after the convergence. What are the benefits we're getting out of it? So this is the post-procurement architect that was in 2011. This is how we used to deliver the services. So giant IP layer on Juniper T series, that was IP service. The routers were not deployed in all the POPs. There were only some POPs where the routers were deployed, which are shown here. Then we had Giant Plus service, which were delivered on Alcatel MCC, as I said before, which was also not in all the POPs, and just some POPs, and it's here. And then Giant Lambda, which is Lambda service, 10 gig wave, it could only support 10 gig, and 40 gig as well, but mainly the Lambdas that we delivered were 10 gig. Only 2 40 gigs were in use, which were for Giant IP purposes, and that was on this layer. So you can already see that we had so many different types of POP. So we had, in these POP we only had STH and DWDM equipment. In these POPs, these were the ones which were fully featured. We had all the services. We could do IP, we could do STH, we could do DWDM, and then here we had 2 POPs where we had IP and STH, and then with 3 POPs with STH only, and then 5 POPs with IP only. So there are a lot of different types of POP supporting different types of services. Post-procurement, so once we post-procurement, post-deployment architect, so 3 main services again. Giant IP now supported in Juniper T and MX. So you can see here we've increased the fully featured POPs by a lot, by 7 or 8, and then IP and switching only, which were 5 only, are now up as well. So there are only 2 types of POP here at this point, rather than 5 different types of POP which have 5 different type of equipment combination and 5 different type of services. We have just 2. So at this stage we were using Juniper T series and MXs to deliver IP service. Giant Plus, the point-to-point service, was only delivered on the Juniper MXs, and Giant Lambda now, which can support up to 100 gig, 40 gig and 10 gig as well, was on the Infinera DTNX, and still is on Infinera DTNX. The 100 gig trunks were delivered on the Juniper MX, so these red lines are the 100 gigs that were delivered, and they were connecting to the Juniper MX. So the IP layer, the Juniper T series, was still not connected using 100 gig. They were still on multiple 10 gigs. MXs were on 100 gig. So we wanted to use 100 gig. We wanted to enable NRINs to connect at 100 gig for Giant IP access. The only way we could do is connect T series using 100 gig as well, or connect the NRINs to the MX. But if we do that, then there are 2 different layers. One is there are 2 separate networks that independently run, different trunks for both. So upgrading Juniper T series or going with 100 gig on T series was very expensive and still is. So we decided to converge the 2 networks so we can provide 100 gig on the Juniper MX to the NRINs. The main reason for that, as I said, we have 100 gig on the MXs, which a lot of capacity there. We need to use it rather than upgrading the Juniper T series. We converge so we can use this. This also enabled us the convergence to provide multiple services on a single interface as a VLAN. As I said, we wanted to give one interface to the NRIN, 100 gig or a 10 gig, and deliver all the services on that if they want to. So they can have IP, point-to-point, multi-point service, layer 3 service. Of course, if they wish to have different interfaces, they can still have it, but if they want a single interface, we can do that. And what we wanted to do was utilize 100 gig trunks that we have put in between Juniper MXs rather than upgrade the IP backbone and spend more money and put more capacity in when the existing capacity is not being used. So this was an exercise to better utilize the available capacity and not spend too much money on upgrading the IP backbone when we have abundant capacity on the switching layer. So what did convergence involve? It involved the convergence of the IP and Giant Plus layer. So all devices in a common IGP, so one big network, not 2 different networks. All devices in the same AS number, the Giant AS number 20965, no difference for switching and for IP. And more importantly, IP and switching services available everywhere. So we wanted to make sure that we can support all the IP and switching services and all the POPs that we have. Obviously the Lambda services we can only support where we have our own dark fiber. We don't have dark fiber everywhere, so we thought at least we could do is we could support IP and switching services on all the POPs. So that's what we did. There were quite a lot of challenges. There were so you can say these challenges or principles. So we had to initially keep Giant Plus and Giant IP traffic separate because we had Giant Plus trunks with 100 gig, Giant IP with just some single 10 gig, some with multiple 10 gig, 4 times 10 gig. So we had to make sure that we don't send all the traffic on one of the paths which is just 10 gig and try and fit in there, and that will result in packet loss. And what we wanted to do is start using the 100 gig for prediction as soon as possible. So as I said, the Infinera migration started in June, July and ended in May this year, but we started convergence in February. So we were in the middle of our DWDM migration when we started the convergence. So not all the trunks were 100 gig, but some were. So when they were all 100 gig, or when a new trunk came as 100 gig, we wanted to start using it as soon as we can. So rather than just leaving it and still using the 10 gig. In the process of convergence, obviously from operations point of view, we wanted to keep both the network running, both the network operational, no black holing of the traffic, and you converge both IPv4 and IPv6, and I'm glad to say that we did the convergence without any major outages or black holing the traffic. And we also didn't want to buy any hardware for T series because we already had quite a lot of interfaces on the Juniper MXS. So we wanted to avoid buying more expensive hardware for the convergence purposes. So this is how the architect was, just post deployment. So you have DWDM and packet transport deployed, and this is how it looked. But then we did convergence, converged the IP, still not enabled it, and then straight away we had IP and packet transport in all these POPs, which enabled us to deliver better features to all the POPs. So at this point we had IP equipment and packet transport as well. And some of the POPs we then decided that only one equipment is fine to deliver both the services. We don't need separate equipment for switching and separate equipment for IP. So we got rid of some of the IP equipment as well. So the advantages for convergence that we see is easier to maintain and manage the network. So now we don't have two different networks to manage, not two different networks to do capacity plan and add capacity onto it. So we have single network, big pipes, 100 gig, and we just do the capacity planning on them. All the point-to-point circuits, all the IP traffic, all the multi-point services, everything run on the single 100 gig that we are using. Obviously they'll be upgraded when we see the traffic is going to a point that we need more capacity. This convergence enabled us to deliver more services to the NREN, allow us to upgrade NRENs to 100 gig. So Janet, for example, upgraded to 100 gig. They were the first NREN, and we delivered that on the Juniper MX, and that was only because we were already ready and we had converged the networks. We were able to deliver the service. It can support, now we can support both IP and GN plus connection on everywhere, bandwidth on demand, point-to-point circuit, multi-point services, IP services on single equipment. And no, we didn't need to upgrade IP backbone, so we didn't need to buy more T series hardware, buy more Infinera equipment to support that 10 gig system. So we just completely started using the 100 gig and avoided upgrading the T series. So the convergence status so far is as I said, in some of the POPs we were able to see that we've got two different equipment doing the same thing, and we can do with one equipment in there rather than using the two. So on majority of the POPs we've moved the connection from T series onto the MXS, and then we have switched off about 9 T series out of 15 in the POPs here, and 3 M series have also been switched off, and this has resulted in quite a lot of savings as well, because the T series are quite expensive to maintain. There is about 110,000 euro per year maintenance cost on that, so this is a lot of saving. There are 4 POPs where we are running both the boxes still, and we see them both the boxes running until we find a solution. They are Vienna, Geneva, Frankfurt and Amsterdam, because there are too many connections in these POPs that one chassis is not enough. So we think if we move to one chassis, all the connection, that chassis will fill up end of 2014 or early 2015, and then we'll need to go out and buy more chassis. So it's better to keep this running. We are looking at different solutions, so maybe a bigger chassis, one single chassis, or maybe just leaving the 2 running, or buying 2 MXs and running them in parallel, but nothing is decided yet. We are still investigating. So this is the post convergence topology for GN. This is very latest topology, so you can see a lot more POP than there were before, and you can connect to any of these POPs and get all the services that we offer, the GN IP, GN plus. Bandwidth on demand is now covered everywhere, so if you want bandwidth on demand here, you can have bandwidth on demand on any of the POP. You just add your interface into the Autobahn, and you can then go to web page, create your own circuit to another NREN which is also subscribing to this bandwidth on demand service. These green lines represent the 100 gigs that we have here. So Western Ring and Eastern Ring have 100 gig. Currently they're running around some of the links around 20%. There are only a few which go sometime above 40%. but at the moment we don't think we need to upgrade any to 200 gig within the next 6 months or so, but we think we may have a requirement for upgrade to Western Ring here, this link especially, and this link maybe by end of next year to 2 times 100 gig. And lastly, in between all the other things that we were doing, we also deployed a Giant Open, an open exchange in London. So we have MX 480 there. The idea of open exchange in London is that the intercontinental links can come into London, connect to this open exchange, and then they can peer with each other as well as Giant. So the benefit for bringing in the circuit to London will be you don't only get Giant, you also get other connectors who are there. So currently there is a connection coming in from China, Orient Plus link, the 10 gig is connected there. SurfNet, NerdNet are connected to exchange point, and ACE link is connected, which is going to mainland in New York. So these are the existing participant. We can support 1 gig connection on this, 10 gig or 100 gig as required, but currently there are 10 gigs on it only because there are not many connector here. Obviously rest of the unrun connected to Giant can get to the exchange point using their point-to-point service, get point-to-point service to London, and then connect to Giant Open. This was launched in October 2012 and was running on a trial basis. We are still trialing. We're looking at how we can add more connection, how we can support more. So we hope in future we see more connection coming into this. So for example, we have connection from South Africa coming into London, that could land here. Connection from Latin America could land here. So we'll have China connecting to Open Exchange, then South Africa coming in from Ubuntu Net Alliance, then US is connecting there, then Giant is connecting there. So it will really open doors for other new networks which are coming in, for regional networks, Middle Eastern networks. They can come connect here and then get all the services, not just Giant. They can get connectivity to US, South Africa, to Asia, to Europe. So this is the idea of the open exchange. In summary, the Giant backbone upgrades are now complete. There is a new equipment and more for all. There is more bandwidth. There is 500 gig super channels on Infinera. There is 100 gig on IP, 100 gig on switching. So you can connect at 100 gig. A lot of bandwidth at our disposal. So come and use this network. More flexibility. So we've got some agreement in place with Infinera, and we're trying to put some similar things with Infinera, with Juniper. So they can deliver us 100 gig interfaces within 15 days. So if we need to upgrade a backbone link, Infinera can deliver interfaces to us in 15 days, not just install them as well. So we can upgrade our backbone if we need to within 15 days. That's obviously Infinera still. We are working on getting the similar thing with Juniper for MXs as well. Maybe get some MX interfaces in stock and we can react quickly. More functions, which is leading to more service offering. So as I said before, it was SDH only point-to-point. Now it's IP and PLS based. A lot of services we can support layer 3 overlays. For example, we are running LHC1, which is layer 3 VPN. We can support VPLS, layer 2 multi-point service, and support all new multi-point VPN services that SA3 Task 3 is working on, which is transparently using Giant backbone to deliver layer 3 VPNs across the Giant domain. Now obviously the open cloud exchange, that functionality we can support in this as well. And more accessibility to Giant user. As I said, the goal of convergence and the migration was to make sure that we can support IP and switching services in all the Giant POP that we have. So that's now done, and this is kind of a real future proofing towards the Horizon 2020. So yes. Oh, thank you for listening, and if you have any question.
Thank you, Mian. Any questions for
We
this?
only have to merge the two presentations into each other, then we are complete.
I'm not familiar with the Infinera VDM platform. You installed 500 gigabit super channel,
Yes.
but is it 5 times 100 subcarrier? How you mix MUX 300G service interfaces
Okay.
from 500.
Yeah, I'm not the transmission guy, but I'm still gonna try and answer the question. So if I get wrong, please, I'll maybe Tony was involved in the infrared equipment. He can correct me if I'm wrong.
Yeah,
So-
I'll correct you if you're wrong.
So we have 500 gig super channel, and then we have PICs we use for 100 gig, and that's all I know. Tony can add to that for infrared equipment.
Well, it's as Mian said, it's photonic integrated transponders. I don't know if you've seen that at any point in time, but this is actually small chips that are combined. But there is there is 10 transponders on one card running 50 gig each. I think the spacing is it 25 gigahertz they are running?
I think 50.
Is it 50?
I think 50, yeah.
50.
Yeah.
Okay, so that's the old version, or older, or less new version. I think the newest one that's coming out will be running 25 gigahertz at a higher rate. But again, it's a closed system, the optical system. You cannot get in contact with it. You can bypass it by installing passive filters, so you can use the fiber that is connected to, but you cannot, in that sense, go into the system. And that's one of the, should we call it, implications or limitations when running alien waves, this special setup. But I can elaborate on that later.
Any other questions? Oh.
It's only have you done a calculation of the savings you've done in the network? By this,
So by this convergence?
yes.
Yeah, so for convergence, we have, I think, saved yearly cost of just over 900,000 euros a year. So that's the saving that we have achieved by doing this. The maintenance contracts were up for renewal in May 2014. We prepaid for that, so we actually got some rebate back as well. So this is not only just saving in future, we also got rebate of what we had already paid.
Yeah.
So the
Annual savings.
annual savings of about 900,000 euros, and when we do find a solution for the rest of the POPs as well, they'll go up to 1.3 million euros from May 2014, hopefully, if we can fix the 4 POPs and decide where we're going. There are new SCBs coming in for the MXs, which can support more per slot. If they can support 200 gig per slot, which the Juniper guys believe they could, then we may not need to 2 chassis and the POP. Then we can just say, okay, fine, we'll move there. Because currently we are using 100 gig one slot only, so that's the way it is. But if 200 gigs can be supported, then obviously we can connect NRENs there and use that way. All right, good, thank you.
Okay. Thank you, Mian. Next speaker is Roeland Nuijts.
Nice.
Now Sienna, former SurfNet. This is more than a year ago.
It is actually about 1 year.
Yeah, it's about 1 year, because you were first time on stage here last year, as I remember.
Simon.
Was that Simon?
Simon.
Yeah, you just joined. You didn't allow him on stage.
Oh.
Okay. You need this one. Put that on your shirt.
Oops.
It's just like the Sienna equipment.
Here. Okay, this is not. Can I put it? It doesn't fit.
Break completely.
It
We
actually-
are having a problem here with the mic.
I can just hold it.
Oh, I think
You get it?
the
Spring.
the springs there.
It's gonna come off again, I think. should go. Is there a pin? This broke off. There was something here.
Yeah, exactly. Well, can we do something? No. We see if we can do some
I don't know
things.
here.
Yeah. Okay. Can you hold it
Yeah.
in your hand until he gets the clip?
Yeah.
Do you need the?
Yeah, the pointer would be good.
Yeah. Do you want to have a?
Oh,
Now it's crash.
what about left or right one? Maybe here.
No, it's just USB. See if it works.
I can just push in here. Should be
Okay.
fine. It has a laser pointer, right?
Yeah, it has a laser pointer.
Okay, thanks for the introduction, Tony. Good afternoon. My name is Roeland Nuijts. I'm with Sienna as a senior system engineer. Indeed, for about the past year. Before that, I was with SurfNet, so I'm quite familiar. A lot of the people I knew already in the R&E community. Thanks for the opportunity to give a presentation. It's always good to be at these meetings and listen to what the requirements are for the R&E community and share what the Sienna vision is. Title of my talk is Future Network Architecture for the R&E community. And I will... This is briefly the outline. So first I will show some networking trends that we considered when we looked at the future architecture. I will discuss our open architecture, which is basically making a very flexible network, which allows users to be connected to content very flexibly, content to content as well. I will get into the details of that. I will discuss our proposal for the optimal converged packet optical architecture. Let's fix the microphone. Yeah, should be okay. And I will discuss the Sienna coherent technology as well, since in the scope of the research plans that we saw, there was also topics on, maximum capacity in big data pipes. And then finally, I will conclude with a summary. So first of all, networking trends. Well, like with everything in technology, you kind of have to step back and just don't look just at what is happening, but why is this happening. So we see in terms of the service trends, we see several things happening. One is the user mobility, which was already discussed today. More and more traffic is going via wireless devices instead of just wired devices. And also different types of connectivity are required, so connections to content. In terms of universities and bigger organizations in the research and education network, we see a lot of demand for cloud services and also vertical integration, for example, for the IT infrastructure that they use. Altogether, this, in terms of capacity, there's also time-based consumption. So you see at certain points of the day, or for example, when you're running large experiment on measurement instruments, you see that between certain points there's a large capacity required. So that means from these service trends you get to connection trends, and basically what we see is that the bandwidth endpoints are moving a lot more than they used to. So your network has to be very flexible to accommodate that. The same goes for connections to data centers, users to content connections, and also content to content. For example, if you, like was discussed before, if you have to move virtual machines from one data center to another. So basically that means that you have to build a much more flexible network, and of course that also has to cost in. You can't just over provision the capacity always to accommodate that needed capacity, because that would be not so cost efficient. To prove these points a bit more, this is actually some results of a market research that Cisco did, and a couple of important points is, while the traffic is still growing very fast, over the past 5 years it grew by a factor of 4, and expectation is that in the next 5 years it will triple again, so the capacity continues to grow. Another important point is that this one, that it is expected by 2016 that actually traffic from mobile devices will be larger than from wired devices. So you can actually see in the network, depending on the time of the day, that your traffic demand is somewhere completely different, and that makes it very important that you can dynamically adjust the capacity in your network. So basically that the network is scalable and also programmable. So this is what we call in Sienna the open architecture. So basically we're moving from connections from silos to silos, like one connection for each application. We're moving to a more dynamic infrastructure whereby you connect the users to the content, or you connect content to content, and you're able to program the network and change it dynamically during the day. And one approach that we think will become very prevalent is the SDN, so software-defined networking. It's been discussed already today, where you have the infrastructure layer, which is talked to by the control layer, and then you have the applications that determine the bandwidth requirements in the network. One of the first applications actually that we support in this is an application that we started to develop already some years ago with SurfNet, which is called DRAC, which you could see as one of the first software-defined networking approaches. And Sienna is very active in the software-defined networking. We are a founding member of the Open Networking Foundation, and we do trials and interworking trials on a regular basis. For example, one is during Vectors this year. Vectors is a couple of weeks of demonstrations that we do in our research labs in Canada, where we show the latest in the technology in terms of transmission, but also in this case of software-defined networking. And this year we demonstrated our software-defined networking demo platform, which is connecting several sites on the East Coast, Chicago, our headquarters in Hanover, and the research labs in Ottawa. And then we do software-defined networking demos on this network to show the potential of this architecture. So in terms of the connectivity, well, a lot of the services that we support is really IP services, but then should we really do all this via routed infrastructure doing the network, or can we do it more efficiently? We think that we shouldn't do it all routed. We actually think that it is better and more cost efficient to use sub-wavelength grooming. So you do IP where it's needed, and you do a mix of packet and optical platform to transport the data actually through the network. So, and in terms of the open infrastructure, this slide shows this more clearly with a couple of the service points here at the top. One, this is the service point where the users are. This is an application server farm, and this is at the application layer. So first of all, from the users to the content, you see that you can have different services, but these can all be transported by the converged packet optical platform. Also here in the core, for example, for moving the virtual machines from one data center to another, also we do this via the converged packet optical core, and these areas in red is where Sienna is active in this arena. So to show you one example of how we implemented this is actually was done at NTT in Japan, where at first they had connections to data centers using a SDH-based approach, but now we implemented this as a packet-based approach, where we can do also time division multiplexing services, but also high packet growth applications. And then in terms of the core side of the network, this is a couple of examples of carriers that are discussing publicly that they also want to move they support IP services, but in terms of the transport, they rather do it not in terms of routing, because it would be too expensive to use. They are interested in using the packet optical converged platforms. So now, what has changed by coherent really in terms of IP technologies? Before, all the connections were done with 10G, and then you can do a lot of meshing. Each pipe is reasonably filled. But when you move to 40 and 100 gig coherent signals, of course you make a much bigger step in terms of capacity. So, and to avoid that some pipes are actually not filled completely, you end up with a partial mesh. So you do less meshing than you would do in the case of 10G. So this slide shows this more clearly. So this is what we would call a local optimum. So actually do full meshing with 100 gig doesn't really make that much sense. You can better do less meshing, and you get the optimal topology here, which is more cost efficient than when you would do full meshing. So you see when you move from 10G to 100G and coherent, you do partial mesh is the most optimum configuration. And the same applies in a way if you if you increase your bandwidth per wavelength. Really, if you go from 10G to 40G to 100G, you see that the optimum amount of meshing actually decreases a little bit for the same reason. But what this really shows is that what really is important is the transit capacity. So if you go to less meshing, that means you have more transit traffic. Then the question is, what will you do with that? Maybe the next slide. So of course, like routers vendors will probably say, okay, you can just use WDM interfaces on the routers and handle the transit traffic there. But actually, we don't think that's the case. It's better to do it, leave it in the optical layer and not do any routing. So that will be actually a more cost-efficient solution. Yeah, and this slide just compares that. So you can imagine when you do a router backbone with basically regions in the router for the express traffic, your cost is a lot higher than when you would do expressing of the traffic when it doesn't need to be terminated. And you can reduce the cost by quite a bit, like in this example, by about 38%. So a few words about the coherent technology itself. As you know, conventional systems basically was on-off keying. So light on is a 1, light out is a 0. And when we move to coherent, you use a bit more sophisticated receiver. So you use a local oscillator that you can use to tune into the information that you need. And by doing that, you can actually extract not only the amplitude, but also the phase information, and actually use two polarizations. So that's how the coherent transmission is done. So actually by going from 10G to 40G, you could actually use the same electronics, but do 4 times as much capacity transmission by using coherent technology. Sienna actually started working on this in about 2005. The first solution was a 10 gig solution with digital signal processing. That was still intensity modulation, dispersion pre-compensation really. So you would send a distorted signal into the fiber, and then by the receive end it would be cleaned up. From this experience, we were able to make the first 40G coherent transmission system, and we were first to market with that in 2008. This was also used for a submarine version, so which is BPSK, so you use only 2 phases and you have more signal to noise ratio margin, so you can bridge the long submarine systems. A slightly faster version was used as 50 gig, and then by using 2 of them in a dual carrier configuration, we were able to support 100 gigabit per second in 2010. So this was not truly a single carrier 100 gig, but it did provide a 100 gig interface for those customers that needed it. At the moment, we are at the 3rd generation, so what we call the WaveLogic 3 family of the digital signal processing chips, and this can do the single channel 100 gigabit transmission. The technology is actually tunable, software configurable, so you can actually use it to do 16 QAM and go to 200 gigabit per second in the future. Here it's shown still as a dual carrier, but at the moment we can also do it in a single carrier and do 200 gigabit per second per carrier. So this slide shows the a summary of the WaveLogic 3 coherent technology. What's very important is the soft FAC, which is adaptable forward error correction, which provides a better margin, so you can go further distances, and you can also use the same technology for the submarine systems. It has a new receiver design, which allows a large amount of polarization mode dispersion compensation up to 50 picoseconds. And what's also important is a digital signal processing at the transmit side. So if you have a linear system, you can do all the compensation basically at the receive end. But as you probably know, most systems are not linear, and then it is actually beneficial to do some of the compensation at the transmit side. So, and this provides that. It also provides some other functionalities, which I will discuss later, which we use for super channel transmission. And then finally, just to give you an impression of the footprint, it's just a one slot card for the 100 gig, and this is the same for, you know, metro, long haul, and also for the submarine applications. So the benefits are really summarized on this slide. First of all, coherent gives you a path to Shannon's limit, so you can actually increase the amount of information you can get into 1 hertz, so increases spectral efficiency. That would not have been possible with intensity modulation. It makes deployment very easy. 100 gig is basically the same as when you did 2.5 gig 20 years ago. It provides you with a programmable infrastructure, so you can actually tune the reach, like you can go from QPSK to 16 QAM. And you can also tune then latency and power, because if you can reduce your FAC, that reduces your latency as well. And that changes your power consumption also. And further, it allows you to build gridless networks, because now you have a local oscillator in your receiver, and you can actually, you know, tune to the particular signal that you would like to detect at the receive side. And this slide shows, the 100 gig made 2.5 gig easy. So years ago, when we did 2.5 gigabit per second transmission, basically dispersion was not an issue. You could go 800 kilometers far without having, you know, to do any dispersion compensation or something like that. When you go to 10 gigabit per second, basically dispersion scales with the square of the bit rate. So at 2.5 gig, you can do 800 kilometers far. So at 10 gigabit per second, you can only do 50 kilometers far. That's of course not sufficient. So if you wanted to go further than 50 kilometers at 10 gigabit per second, you had to add all these dispersion compensators to compensate for the dispersion in the link. And you had to add additional amplifiers to compensate for the loss in the dispersion compensating fibers. And for every system, basically, you had to do quite extensive simulations to determine, you know, what's the optimum dispersion compensation. And also, like, this path goes from A to B, let's say. There may be another signal that is actually added as amplifier and goes another path, and also that path has to be optimum in terms of dispersion compensation. Now, going to coherent transmission, actually we're back at the simplest designs of before, since because of the digital signal processing, you know, you can compensate for a large range of dispersion, and you can compensate for a large range of polarization mode dispersion, and that makes it very easy to put these systems together. So the 100 gig design is as simple as the 2.5 gig design. This is an example of how you can make your infrastructure programmable. So let's say, for example, you set up a link via this fiber pair with a certain length, and this would consume this amount of power. You have a certain latency and a certain maximum reach. But now, if this link turns out, to be shorter, you can actually, you know, reduce the FAC. Your latency becomes less. Your reach goes down, but it's still sufficient for this link, and your power consumption goes down as well. So as such, you can provide a programmable infrastructure. Now, if this fiber breaks, you can actually, you know, increase the FAC, so you can do the longer distance, and although a little bit smaller capacity, you can still serve this, connect these two sites.
Do you have to do it manually or could it be done?
At the moment, it can be done by the management system, but it's not at this moment, but in a future release. Yeah, yeah, yeah. Then in terms of moving to higher speeds, you basically have three dimensions that you can use. One is go to a more complex constellation, so more phase information in each symbol. One is increase the symbol rate, and one is to add more subcarriers, which we did some experiments with to do high speed transmission. This is actually one of the aspects of the advantages of the transmit side digital signal processing that I mentioned before. So you can actually do pulse shaping, and that actually makes your spectrum look more like a square, and by doing that you can actually move the signal spectra very close together and get a high spectral efficiency. So this is a technique we used, for example, to do a 1 terabit per second transmission experiment in the lab. And recently we also have done this in the field with one of the networks that we built, which is Comcast in the US. This is a cable provider, and we did a trial over 1,000 kilometers of distance using 16 QAM and then achieving 1 terabit per second transmission. So this is one field trial we did. This was actually accompanied alongside by 10 gig on-off keying signals and also other 40 gig and 100 gig coherent live traffic. So this was quite a successful trial, and the Comcast submitted a press release about this. Just a little bit on the alien wavelengths. Well, since coherent is so tolerant against dispersion and polarization mode dispersion, it's of course very attractive to use it for alien wavelength experiments. So while we've done some in the past, SurfNet and NorthernNet actually is still using an alien wavelength between Amsterdam and Copenhagen. And you know, in Siena has, since the performance of the coherent systems is quite good, they are used a lot to upgrade submarine cables, and then in essence they're all alien wavelengths. So then this is one example, Farwise here in the area where we did a upgrade of a 10 gig cable to 100 gig per channel over 2,300 kilometers, and that is, you know, in essence an alien wavelength. It goes over this is an Alcatel system, and then on the terrestrial side it goes over a Marconi system. So this is also an end-to-end alien wavelength, and yeah, that is just because of the large tolerance of coherent. It is very suitable for these kinds of deployments. And of course that will save you in capex because you don't need to regen, and it saves also in operational expenses because it's much easier to install since you only need to install equipment at the endpoints. So to summarize, we see with the continuing growth in traffic and with the move of, or the growth of mobile traffic also, we see a shift towards users to content and content to content traffic in the network. We believe that the packet optical platform is the way to go to transport the signals. You don't need to do IP everywhere, and this is effective both in aggregation, so at the access side, and also in the backbone of the network. And looking at all these topics and this architecture that we envision, if you compare that to the scope of the research that is defined in the JRA1, I think we're very well aligned with that, and we are keen to work with you on that. So with that, I would like to conclude. So thank you for your attention. Yeah.
Thank you, Roeland.
Are there any questions? Or?
I have one. You mentioned that the system you are building with NorthernNet between Helsinki and London, maybe you needed one regeneration point due to because you have some long span.
Yeah.
Did you make any simulation based on to find out how total OSNR changes regarding the amplifier this span actually, the distance?
Well, we have a tool that is actually available to us as system engineers, but also for the customer, the user of the network. And in there you can define all the span lengths, where are the amplifiers, and you can run the simulation of the 100 gig channels. You define all the channels that are in the network, and then it will actually give you the OSNR that is delivered at the receiver, and also the OSNR that is needed for that distance, because if you have a longer distance, you have more distortion, and you do see that the required OSNR increases a little bit. But from those two values, you can see how much OSNR margin that you have.
What maybe is beneficial for us in GRA1 in this task we are running is to have a simulation of it, to analyze actually how total OSNR actually varying when you have different amplifier distance.
Like spacing.
Spacing.
Yeah.
Then, like it OSNR as a function of amplifier spacing. For a given length.
Yeah, you can actually, in a way it's a linear model, right? And you can actually approximate it with quite a simple formula.
Yeah.
So, and that shows you, for example, well, let's say you have a given system with 10 spans, and if you would double that system, basically your OSNR goes down by 3 dB.
Could we have runs together some?
Yeah, we can, sure. Yeah, we can discuss sometime.
Have some as a poster or trainer from actually?
Yeah, this is kind of related of that earlier figure of merit work that we did. It's kind of similar, so, but we can, so maybe a poster will not be possible, but but we can go through it if you like. Yeah. Are there any other questions? Okay. Thank you for your attention.
Thank you. Although that we are running late, we asked the remote presenter to be ready at 3:30, so we have approximately 12 minutes or something like that. But I can ask him if he could dial in right now.
Online?
Yeah, he's online. Okay. I guess he can. I guess he